In 1977, NASA launched two spacecraft that were originally expected to operate for only a few years. Their mission was simple: fly past Jupiter and Saturn, transmit scientific data back to Earth, and fade into history. But instead, NASA sent humanity on the longest journey we have ever undertaken. Today, Voyager 1 is more than 150 astronomical units away from the Sun. It has already crossed the heliopause, the boundary where the influence of the solar wind ends and the interstellar medium begins. And it was there that something unusual happened. Its instruments recorded a sudden change in plasma density. Magnetic fields abruptly shifted in character. Levels of cosmic radiation increased. Voyager saw nothing with its eyes, yet the physics of space around it had clearly changed. This marked humanity's first direct encounter with interstellar space. But here is an important detail. Even now, after nearly half a century of flight, Voyager still remains within the Sun's gravitational sphere. It has left the bubble of the solar wind, but it has not yet left the solar system. Between Voyager and the true boundary of our system lie thousands of years of travel. And it is there, in near complete darkness, that a hypothetical structure we have never directly observed is believed to exist. A vast sphere made of trillions of icy bodies, a cosmic graveyard of primordial matter, and the distant source of the comets that occasionally light up our skies. We call it the Oort Cloud. Everything began with a launch. In that moment, a fragile machine of extraordinary precision set out on a journey no one had ever attempted before. Voyager 2 was not just another spacecraft. It became humanity's first envoy to the outer planets. A silent observer sent to uncover the secrets of worlds we could barely imagine. Its trajectory carried it past gas giants and icy moons, revealing environments so strange they seemed almost alien. The data it transmitted back to Earth forever transformed our understanding of these distant worlds. Voyager revealed the raging storms of Jupiter, the intricate rings of Saturn, and the supersonic winds of Neptune. Yet it was the brief encounter with Uranus, the least explored of the giant planets, that left us with some of the greatest mysteries, secrets hidden within the planet's magnetic field, its moons, and its unusual axial tilt. Voyager's journey ended decades ago, but its discoveries still shape the questions we ask today. And now, by re-examining its data with modern technology and fresh scientific perspectives, we are uncovering new insights about these worlds, especially Uranus, that Voyager itself could never have imagined. The 1986 flyby of Uranus by Voyager 2 became a milestone in the exploration of the outer solar system. For the first time, humanity observed this distant and mysterious planet up close. Its blue-green color, its faint rings, and its extraordinary axial tilt, which causes Uranus to orbit the Sun almost like a rolling ball. Yet behind the stunning images and data gathered during that encounter lie findings suggesting that our understanding of Uranus, particularly its magnetosphere, may need to be reconsidered. Voyager 2's journey to Uranus occurred under rather unusual circumstances. The spacecraft arrived only days after a rare and powerful burst of solar wind. This surge of high-energy charged particles from the Sun compressed the planet's magnetic field to a fraction of its normal size. Solar wind, a continuous stream of charged particles flowing from the Sun, normally shapes planetary magnetic environments, creating magnetospheres that shield worlds from harmful solar radiation. But in this case, the solar wind was so intense that it compressed Uranus's magnetosphere to about 20% of its usual volume, significantly distorting the measurements the spacecraft was able to collect. According to a recent study published in Nature Astronomy, such conditions occur only about 4% of the time. Had Voyager arrived just a week earlier, it would have observed a much larger magnetosphere, more similar to those of other giant planets such as Jupiter, Saturn, and Neptune. Previously, scientists believed that Uranus's magnetosphere was unusually weak, with low plasma concentrations and extremely energetic radiation belts. Plasma is a state of matter in which atoms split into charged particles. It is a common feature in the magnetospheres of many planets, especially those with strong magnetic fields. Voyager's data suggested that Uranus's magnetosphere contained almost no plasma from either the solar wind or its moons, making its plasma environment appear exceptionally sparse. However, new analysis points to a different conclusion. The solar wind likely temporarily suppressed the presence of plasma in the planet's magnetosphere, leading to the mistaken impression that Uranus lacked significant plasma altogether. At the very edge of our solar system, far beyond the orbit of Pluto, there may exist a vast invisible structure. Imagine a spherical shell of space populated by billions or perhaps trillions of ancient icy objects. This swarm of bodies forms the most distant boundary of the Sun's influence. It appears in nearly every diagram. Scientists speak of it as something almost taken for granted, yet there is one paradoxical detail. We have never seen it, not once. Humanity knows even less about it than about some nearby star systems. So why are scientists so confident that it exists? And what if they are mistaken? What do the orbits of ancient comets, decades of astronomical calculations, and recent discoveries truly reveal? Could other star systems hide similar structures? Or have we misunderstood something fundamental about our own solar system? Every time a comet passes close to the Sun, part of its icy surface evaporates, creating the beautiful tail that we observe. However, there is one important detail. If a comet repeatedly approaches the Sun, its ice should eventually be exhausted. So where do these comets come from? And how do they manage to survive for billions of years? Astronomers concluded that comets spend most of their existence far from the Sun's heat, in a kind of deep freeze reservoir at the outer edges of the solar system, and only occasionally travel into its inner regions. Another important clue came from the orientation of cometary orbits. Unlike the planets, most of which move in nearly the same plane, and unlike the short-period comets from the Kuiper belt, many long-period comets appear from different directions at a wide range of angles. These icy wanderers can arrive from above, from below, or from almost any direction relative to the planetary plane. Such random orbital inclinations suggest that their source is not a flat disk like the asteroid belt or the Kuiper belt, but rather a distant spherical reservoir surrounding the Sun. By the middle of the 20th century, all the conditions were in place for the proposal of a bold hypothesis that could explain this mystery. As early as 1705, the English astronomer Edmund Halley determined that the bright comet observed in 1607 and 1682 was actually the same object, returning on an orbit with a period of about 75 years. Today it is known as Halley's Comet. This discovery proved that at least some comets repeatedly orbit the Sun and raised a profound question. How could Halley's Comet return for thousands of years without disintegrating? The logical answer was that it spends most of its time far from the Sun, preserving its ice in the deep cold of space. Let us move forward to 1932, when the Estonian astronomer Ernst Öpik proposed a bold idea. Perhaps a vast cloud of cometary bodies exists at the outer edge of the solar system, serving as a reservoir that replenishes comets. This concept remained largely unnoticed until 1950, when the Dutch astronomer Jan Oort independently arrived at a similar conclusion, now supported by new observational data. Oort studied long-period comets, those that orbit the Sun over thousands or even millions of years, and noticed something unusual. The farthest points of their orbits, known as aphelia, tended to cluster at a distance of about 50,000 astronomical units from the Sun. That is roughly 4.5 trillion miles, an almost unimaginable distance, yet still within the gravitational influence of our Sun. These comets were not arriving from interstellar space. They were far too close for that. But it was also clear that they did not originate from any known region of the solar system closer to Earth. For Oort, The data pointed to the existence of a vast cloud of icy bodies orbiting the Sun at distances of tens of thousands of astronomical units. In his 1950 paper, he proposed the theory of a thick spherical shell of icy debris surrounding the solar system. This idea elegantly explained two things at once: why long-period comets arrive from all directions and where they reside when they are not visible. The hypothetical cloud of comets soon became known as the Oort Cloud or the Oort Cloud. Although Oort's hypothesis was quite radical for its time, it has withstood decades of scientific scrutiny. Even though we have never directly observed the Oort Cloud, it remains the leading explanation for the origin of long-period comets, supported by extensive calculations and modern computer simulations. But to understand how unusual the Oort Cloud is, we must first recall the structure of the solar system as we know it. The planets, from Mercury to Neptune, orbit in nearly the same plane, known as the ecliptic. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky debris. Beyond the orbit of Neptune, roughly 30 astronomical units from the Sun, lies the Kuiper belt, a vast ring of icy bodies and dwarf planets such as Pluto, extending out to about 50 astronomical units. Both the asteroid belt and the Kuiper belt are disc-shaped structures confined to the ecliptic plane, orbiting in the same direction as the planets. On a cosmic scale, these regions are still relatively close to our star. Beyond the outer edge of the Kuiper belt, the solar system does not end abruptly, but it becomes extremely sparse. Here begins a lightly populated region known as the scattered disk, which extends several hundred additional astronomical units outward. Data from New Horizons, a mission of NASA, suggests that some Kuiper belt objects were gravitationally scattered onto highly elongated orbits that may reach distances of around 1,000 astronomical units. Yet even at 1,000 astronomical units, we have traveled only about 1% of the way toward the proposed Oort Cloud. The inner Oort Cloud is believed to begin roughly 2,000 to 5,000 astronomical units from the Sun. The main body of the cloud may extend out to 50,000 astronomical units or even farther. Numbers like these are truly difficult to comprehend. For comparison, 1 astronomical unit is the distance between the Earth and the Sun. 50,000 astronomical units equals roughly 0.8 light-years, almost 1/5 of the distance to the nearest star. According to some estimates, the most distant parts of the Oort Cloud may extend to 1.5 light-years, or more than 100,000 astronomical units. In fact, this structure could stretch anywhere from a quarter to half the distance to the nearest star. That is precisely why it is considered the most distant region of the solar system. Even the fastest spacecraft ever built by humanity would require thousands of years to cross such distances. For example, the probes Voyager 1 and Voyager 2, launched by NASA, are farther from Earth than any other human-made objects. After more than 48 years of travel, by 2026, Voyager 1 is about 159 astronomical units from the Sun, far beyond the orbit of Pluto, yet still nowhere near the Oort Cloud. At its current speed of roughly 17 kilometers per second, Voyager 1 would reach the inner edge of that cloud in about 300 years, and traveling across it entirely would take nearly 30,000 years. By that time, its instruments would have long since stopped working. In other words, even if future scientists were to send a dedicated probe to this structure, they would never live long enough to witness its arrival. The scale of this cloud is not merely enormous, it is almost interstellar in extent. Imagine an ancient icy wanderer that spent tens of thousands of years drifting through the frozen darkness at the very edge of our solar system. and is now heading straight toward us. In 2025, the automated telescopes of the Pan-STARRS first detected the faint glow of this distant object. Since then, it has been gradually moving closer to the center of our solar system, toward the Sun itself, and toward Earth. This object, named Comet C/2025 R3, is remarkable not only because of its trajectory, but also because of its possible fate, as it may soon become one of the most impressive celestial spectacles of the year. According to astronomers' calculations, on April 20th, 2026, the comet will reach perihelion, its closest point to the Sun, at a distance of about 0.51 astronomical units, or roughly 100 million kilometers from our star. A week later, on April 27th, it will make its closest approach to Earth at a distance of approximately 0.53 astronomical units. This is still a completely safe distance, but close enough for the comet to potentially become visible in the night sky. The orbit of Comet C/2025 R3 is also quite unusual. It is tilted by about 125 degrees relative to the ecliptic plane, meaning the comet travels in a retrograde direction, opposite to the motion of the planets. Such steeply inclined trajectories are a classic signature of bodies originating from the distant Oort Cloud. In addition, the comet's position between the Sun and Earth could create an interesting visual effect. Its dust tail may reflect sunlight directly toward our planet, transforming what would normally be a faint object into a bright glowing streak across the sky. Under favorable conditions, it might even become visible to the naked eye if the comet's nucleus releases enough dust. So when you look up at the night sky in the spring of 2026, remember that this visitor from the Oort Cloud is more than just a beautiful sight. It is a window into the earliest history of our solar system, an icy messenger arriving from its most distant and barely explored regions. Now let's take a closer look at what we know about the solar wind. When these charged particles interact with a planet's magnetic field, they exert pressure capable of compressing, expanding, or even reshaping the planet's magnetosphere. This interaction is far from constant. The properties of the solar wind continually change under the influence of several factors, including solar activity and the planet's distance from the Sun. On planets with strong magnetic fields, such as Earth, Jupiter, and Saturn, the solar wind can significantly shape their magnetospheres, forming powerful protective shields that help guard the planet from harmful radiation. A magnetosphere is essentially a planet's natural defense system, created by its internal magnetic field. It functions as a shield that deflects and redirects charged particles away from the planet. However, this system is not completely impenetrable. The strength and size of a magnetosphere depend largely on the dynamic pressure of the solar wind, which varies depending on the wind's speed and density. When the spacecraft Voyager 2 performed its flyby of Uranus in 1986, conditions were particularly extreme. The dynamic pressure of the solar wind was close to its peak. The dynamic pressure of the solar wind is calculated as the product of its mass density and the square of its velocity. Under normal circumstances, the magnetosphere of Uranus extends roughly 22 to 25 planetary radii from the planet. During the flyby, however, the magnetopause, the boundary where the pressure of the solar wind balances the planet's magnetic pressure, was compressed to about 17.3 Uranian radii. As the solar wind pressure increased in the days leading up to the encounter, the overall size of the magnetosphere shrank considerably. This compression influenced not only the magnetopause, but also likely affected the unusual behavior of the planet's radiation belts. Normally, radiation belts around planets are formed from plasma originating in the planet's atmosphere, its moons, and the solar wind. During Voyager 2's approach, the intense solar wind probably pushed plasma out of the magnetosphere of Uranus, leaving the region significantly depleted and altering the typical behavior of its radiation belts. As a result, an unexpectedly powerful belt of electron radiation appeared, a phenomenon that puzzled scientists for decades until more recent studies offered possible explanations. Astronomers have also proposed that the Oort Cloud may actually consist of two distinct regions. Its outer portion forms a classic spherical shell extending roughly from 20,000 astronomical units out to distances of 50,000 astronomical units and even farther. Objects in this outer region are only weakly bound by the Sun's gravity, and over millions of years their orbits have spread out to form a gigantic spherical cloud. Closer to the Sun, however, there may exist a denser inner Oort Cloud, often referred to as the Hills Cloud. This region is thought to extend from roughly 2,000 to 20,000 astronomical units. Scientists believe this inner region could have a more disk-like or toroidal structure, somewhat resembling a puffed-up version of the Kuiper belt. Objects within this inner cloud remain slightly more strongly bound to the Sun's gravity and may not yet have fully dispersed into a spherical distribution. Instead, they may form a dense disk or ring of material beyond the scattered disk region. Why do astronomers think there are two separate regions? One explanation lies in gravitational binding. Objects located only a few thousand astronomical units from the Sun still feel a strong enough gravitational pull from the star to remain in a relatively flattened distribution. In contrast, bodies located extremely far away, more than 50,000 astronomical units, are so weakly bound to the Sun that passing stars and the tidal forces of the galaxy can scatter them in all directions. Computer simulations support this idea. They suggest that during the early history of the solar system, close stellar encounters and the tidal gravity of the Milky Way may have disrupted the orbits of distant planetesimals. These interactions likely rounded the orbits of the most distant objects, forming an almost spherical cloud, while the inner region, being more tightly bound to the Sun, managed to preserve a more primordial disk-like structure. In short, the Oort cloud may consist of an outer spherical shell and an inner toroidal band that coexist as part of the same structure. Together, this two-layered region could contain an immense number of icy bodies, ranging from tiny comet nuclei only a few kilometers across to far larger and more massive objects. But what exactly are the objects in the Oort cloud made of? Based on the comets we have been able to observe, the vast majority appear to be mixtures of ice and dust. In simple terms, they are often described as dirty snowballs. Scientists believe that the bodies within this cloud are composed of volatile ices, such as water, carbon dioxide, methane, ammonia, and carbon monoxide, combined with rocky material and complex organic compounds. Estimates suggest that the cloud may contain hundreds of billions, or even trillions, of such icy objects. Many of them are relatively small, though some could reach tens of kilometers in diameter or more. A few researchers have even suggested that among them there may be bodies large enough to qualify as dwarf planets, but we will return to that idea later. Until recently, nearly all known objects arriving from the Oort cloud were icy and revealed themselves as comets when approaching the Sun. However, in 2021, astronomers received an unexpected surprise. A bright fireball meteor, observed over the province of Alberta in Canada, was traced back to the outer regions of the solar system. To everyone's surprise, it was not made of ice, but of rock. This meteoroid, roughly the size of a grapefruit, penetrated the atmosphere of the Earth much deeper than an icy comet fragment normally would, indicating a much greater density and a rocky composition. Its orbit turned out to be strikingly similar to that of a long-period comet, with a steep inclination and even retrograde motion. These are exactly the characteristics one would expect from an object originating in the Oort cloud. Scientists were therefore puzzled. Despite its place of origin, this object was rocky, contradicting the long-standing assumption that the cloud contains only frozen material. How could this happen? The most widely accepted theory suggests that during the early stages of the formation of the solar system, some rocky bodies from the inner regions were ejected through gravitational interactions and later mixed with the icy population of the Oort cloud. In fact, Recent research indicates that a few percent of the cloud's population may consist of asteroids, rocky objects, rather than purely cometary bodies. But if the Oort cloud contains trillions of objects, why have we never directly observed a single one? The answer is simple: distance and faintness. Most objects in the cloud are only a few kilometers in diameter and lie at such enormous distances that detecting them requires a level of resolution beyond the capabilities of modern telescopes. A typical Oort cloud object may be no larger than a mountain, yet it is located at a distance from the Sun that is more than 50 million times greater than its own size. It would be like trying to see a snowball from tens of billions of kilometers away. Even the nearest objects would appear incredibly dim. Unlike stars, which emit their own light, or planets closer to the Sun, which reflect enough sunlight to be detected, the bodies of the Oort cloud are dark and inactive. In practice, they are almost completely invisible against the black background of space. Moreover, even today we can barely observe dwarf planets in the Kuiper belt, located about 50 astronomical units from the Sun and measuring hundreds of kilometers across. And even those objects still reflect some sunlight. Beyond the Kuiper belt, even the combined glow of billions of comets from the Oort cloud would be far too diffuse and faint to detect. Given such vast and largely unexplored territories in the outer solar system, it is hardly surprising that scientists and dreamers alike have speculated about unknown planets hiding out there. One well-known hypothesis proposed the existence of a giant planet nicknamed Tyche, suggested in 1999 by two astrophysicists. They noticed small irregularities in the orbits of several long-period comets and proposed that these disturbances might be caused by a hidden gas giant, possibly several times more massive than Jupiter, located somewhere within the Oort cloud. According to the hypothesis, Tyche might orbit at a distance of 10,000 to 20,000 astronomical units. However, the idea remained purely speculative. In 2010 and 2011, NASA's infrared space telescope WISE conducted a full-sky survey capable of detecting large cold objects even at enormous distances. The telescope found no evidence of a planet the size of Jupiter or larger in the outer solar system, effectively ruling out the existence of Tyche. Nevertheless, the concept of hidden worlds at the edge of our system continues to appear in other hypotheses. In recent years, astronomers have actively discussed the possible existence of the so-called Planet 9, also known as Planet X, a potential super-Earth or mini-Neptune with a mass roughly 15 times greater than that of the Earth. It is thought that such a planet, if it exists, might orbit near the inner edge of the Kuiper belt. But that is a completely different story. And by the way, we have already made a separate video about it. Still, one question remains open. Could there be planet-sized objects hidden within the Oort cloud? It is not entirely impossible. A 2023 study examined the issue from another perspective: the capture of wandering planets. Computer simulations suggest that when stars form within stellar clusters, as the Sun once did, they can capture planets that were ejected from neighboring planetary systems. These captured worlds typically end up on the outskirts of their new star system, essentially within the region of the Oort cloud. Researchers estimate that the probability that the Sun captured an ice giant-sized planet early in its history is about 7%. And it is entirely possible that such a planet could still be hiding deep within the Oort Cloud, a kind of adopted world of our solar system. Interestingly, researchers have also concluded that such a planet would be more likely to have been captured as a rogue world from another star system rather than ejected from the Sun's original planetary system. They estimate that the probability of one of the Sun's primordial planets being thrown out to the distant outskirts of the system is only about 0.5%. Even so, a probability of 7% still means that it is entirely possible that no large planets exist there at all. At present, we have no direct evidence for any massive object within the Oort Cloud. If such a body existed, we would probably have already detected subtle gravitational disturbances or a faint infrared signature. Yet even though the cloud itself remains essentially invisible to us, it communicates indirectly through the comets that occasionally travel from its depths into the inner solar system. Among astrophysicists, it is widely accepted that long-period comets, whose orbital periods exceed 200 years, originate in this distant region. Some of the most spectacular comets ever recorded in history belong to this category. These are brilliant celestial visitors that seem to appear from nowhere and may not return for thousands of years, or sometimes never again. When a distant object from the Oort Cloud receives a gravitational push, perhaps from a passing star or from the slow tidal forces of the galaxy, it can begin a long inward journey toward the Sun, following a stretched, elliptical orbit. After millions of years, such an object eventually reaches the inner solar system, appearing to us as a completely new comet. On the scale of a human lifetime, these events appear rare, but over millions of years, there is a continuous flow of comets moving through our planetary neighborhood. Most long-period comets that astronomers have observed have appeared only once in recorded history. Their orbital periods are so immense that entire civilizations may rise and fall between their visits. Some comets travel along such extended orbits that the last time they passed through the inner solar system, modern humans had not yet appeared on Earth. Others follow trajectories that ensure they will never return at all. In those cases, the Sun provides a final gravitational slingshot, sending them outward beyond the solar system and turning them into interstellar wanderers. An interesting subgroup is the Halley-type comets. These objects have intermediate orbital periods, typically between 20 and 200 years, yet their orbits are often highly inclined or even retrograde. They are named after Halley's Comet, which, despite its roughly 75-year period, is believed to have originally come from the Oort Cloud long ago. Scientists think these bodies may have started as long-period comets, whose paths were later altered through gravitational encounters with the giant planets, particularly Jupiter. This explains why Halley's Comet and similar objects do not orbit along the plane of the ecliptic like most short-period comets. They were not born in the Kuiper belt, but rather in the Oort Cloud, and were only later redirected toward the inner regions of the system. Still, an intriguing question arises. Could some long-period comets actually originate beyond the Oort Cloud, outside our solar system entirely? In fact, the answer is yes. The first confirmed interstellar comet, 2I/Borisov, was discovered in 2019. It followed a hyperbolic orbit, meaning it was not gravitationally bound to the Sun. Its chemical composition, particularly the high abundance of carbon monoxide, suggests that it formed around a different type of star. Even earlier, in 2017, astronomers detected an even more mysterious object, Oumuamua, another visitor from interstellar space. These discoveries demonstrate that some comet-like objects truly originate beyond our solar system. However, such visitors are extremely rare. The overwhelming majority of long-period comets display characteristics that match perfectly with an origin in the Oort Cloud. Their orbital distribution, their inclinations, and the fact that we observe far more long-period comets than interstellar ones all strongly support the idea that this distant cloud really exists and is populated with objects. Every long-period comet that graces our skies, sometimes only once in a lifetime, is essentially a messenger from this dark and remote region, offering indirect proof of its existence. Earlier, we mentioned that comets from this cloud can arrive from almost any direction, forming a nearly uniform sphere surrounding our star. This spherical structure is one of the key features of the Oort Cloud hypothesis. But why a sphere rather than a flat disk like the planetary system itself? The answer lies in billions of years of gravitational influences. In the early solar system, the precursors of the cloud were planetesimals, small building blocks of planets that were flung outward by the gravity of Jupiter and the other giant planets. At first, these objects traveled along elongated orbits that still roughly followed the plane of the original protoplanetary disk. Over time, however, two major factors gradually randomized their orbits: passing stars or galactic tidal forces. Our Sun was born within a stellar cluster, which means that during the first hundreds of millions of years, neighboring stars frequently passed relatively close by. Even today, such encounters occasionally occur. For example, Schultz's star passed about 70,000 years ago at a distance of roughly 0.8 light-years, brushing the outer edges of the Oort Cloud, fortunately without causing major disruption. Encounters like this, combined with the constant, though weak, gravitational influence of the Milky Way, gradually alter the orbits of distant objects. Computer simulations conducted by researchers, including Alessandro Morbidelli, have shown that these effects eventually lead to a random distribution of orbital inclinations within the Oort Cloud, transforming its original disk-like structure into a nearly isotropic sphere. The outer Oort Cloud, which is only weakly bound to the Sun, was especially vulnerable to these influences and eventually became almost completely spherical. By contrast, the inner region, known as the Hills Cloud, remains more strongly bound to the Sun's gravity and may never have become fully spherical, possibly retaining a somewhat flatter shape. In other words, the spherical form of the cloud is the natural result of billions of years of gravitational interactions originating far beyond the solar system. This leads to another fascinating question. If our Sun has an Oort cloud, do other stars have them as well? Astronomers believe that similar structures should be a common byproduct of planetary formation. The same processes, giant planets ejecting comets and stellar encounters reshaping distant orbits, are expected to occur in other planetary systems as well. Many scientists therefore suspect that numerous, perhaps even most stars with planets, possess their own vast cometary halos, often referred to as exo-Oort clouds, and in fact, indirect evidence for their existence is already beginning to emerge. When astronomers observe comets plunging into other stars, or detect debris disks with extended structures surrounding them, it suggests that those systems also contain distant reservoirs of icy bodies. In fact, during its early history, Our solar system may even have exchanged material with neighboring stellar systems. However, directly detecting exo-Oort clouds is extremely difficult, for the same reasons that we cannot clearly observe our own Oort cloud. Still, astronomers have already proposed several intriguing ideas. In 2018, a group of astrophysicists suggested that a large Oort-like cloud around a nearby star might leave a faint imprint on maps of the cosmic microwave background. The concept is that a distant shell of extremely cold dust and ice could slightly absorb or emit microwave radiation, creating a tiny shadow or a faint glow detectable through highly precise observations of the cosmic microwave background. By analyzing data from missions such as Planck, researchers hope to uncover traces of similar structures around other stars. After all, if a cometary cloud formed during the birth of our solar system, it is reasonable to assume that comparable structures may exist throughout the galaxy. Each of these would represent a kind of invisible cocoon of material, a relic of the planet formation process and a distant source of comets that occasionally travel toward their parent star. So what can we really say about this enormous and mysterious structure? At the very least, it represents one of the most fascinating paradoxes in modern astronomy. We are dealing with a colossal structure that cannot yet be seen directly, yet whose existence scientists are largely confident about. It is a powerful demonstration of how scientific reasoning works. Just as the existence of Neptune was predicted before it was ever directly observed, the astronomer Jan Oort inferred the presence of this remote region by studying patterns in the orbits of comets. Today, that idea continues to gain strength as new evidence suggests that something truly exists there, even if it remains hidden from our direct view. At the beginning of the 21st century, humanity still has not launched a space probe capable of reaching this distant region, nor have we built a telescope powerful enough to photograph its objects directly. But the next time you see a comet lighting up the night sky, take a moment to think about where it truly came from. Somewhere in the deep darkness of space lies a vast cosmic halo that, although almost invisible, helps us understand where our planetary system originated and how it fits within the immense Milky Way galaxy. Thank you for watching. If you enjoyed this journey to the farthest edges of our solar system, don't forget to subscribe to Hubble and turn on notifications so you never miss a new exploration of the universe. There is still so much we don't know about the cosmos, and together we will continue discovering its mysteries. See you in the next video.